Hi, my name is Patrick Geneva, and today I will be presenting our work entitled Map-Based Visual Inertial Localization, a Numerical Study. The key motivation of this work is to investigate how to leverage prior map information to improve visual inertial estimation methods. In particular, we investigate 3D point-based prior maps, which use 2D to 3D measurement models, and keyframe-based maps, which leverage a 2D to 2D model. The main contributions are as follows. We summarize the different techniques for incorporating loop closures efficiently, including their use in an extended Kalman filter, which tracks and updates all correlations with the map, a Schmidt-Kalman filter, which tracks the correlation with the map but does not update the map state estimates, and through measurement inflation models, which do not track any correlation, do not improve the map estimates, and require the injection of noise to not become overconfident. All methods are applied to the two different prior maps and compared in terms of their accuracy, consistency, computational complexity, and memory usage. We will now go into a bit more detail on the two different map representations to provide a bit of background. We have a basic filter-based odometry system which keeps track of a sliding window of historical poses that observe environmental features. In this case, the pose 1, 2, and C observe the feature and provide a set of bearing measurements to it. For point-based maps, we leverage a 2D to 3D measurement model. In this case, the map has the 3D position of the feature, and thus we directly write our measurement as a function of it. For the keyframe-based map, we instead leverage historical observations such as Z0 and Z1. These measurements are observed from prior map keyframe poses K0 and K1, which are contained within the map state. Thus, in this case, we have two additional measurements that we use to update the state. We note that we remove the dependency of the measurement function on the 3D position of the feature through MSCKF null space projection. For the sake of time, we will summarize the detailed simulations performed in the paper. We first investigated how different quality of prior maps affect localization performance. Shown on the table on the right, both map types still improve estimated performance even at very high noise values. We found that point-based maps provide the most accuracy improvements, which is likely due to them being a more direct constraint compared to a 2D to 2D additional bearing measurement model. Keyframe-based maps still improved the performance and had an advantage of being more computationally cheaper for a large number of feature tracks. The Schmidt-Kalman filter was computationally efficient and can provide very consistent estimation. And finally, inflation-based methods are relatively invariant to their inflation parameters and can provide consistent and efficient performance on large-scale maps once they're tuned. Finally, we have the following recommendations. The SKF should be leveraged for small workspaces to achieve high accuracy and consistent estimation. Keyframe-based maps can be leveraged to reduce the computational demands of the prior map. And finally, for large environments, inflation methods can be leveraged with conservative parameters with great success. In the future, we will evaluate on larger scale real-world datasets and on resource-constrained platforms. Thank you.